this video, we're going to be looking at, I think, one of the coolest calculus theorems. This is the mean value theorem. And before we get started with this, here are just some questions that I would like you to do on your own. So pause the video and do this question. So in other words, given this function, sketch it, find the slope of the secant line between these 2 points, and then find a point on the graph in between those x values that has the same instantaneous slope, and draw a tangent line on this graph. So if you know what to do, go ahead. Otherwise, just if you know what to do, pause the video, try to do this. Otherwise, just follow along with me. Okay, so at -2, we've got this point, -2, -3. And at 2, we've got the point 2, 5. And if we want to find the slope of the secant line, well, let's first draw in that secant line. And the slope is going to be the change in y, which is 8, over the change in x, 4. So the slope is 2. And then it says find a point or points on the graph in between x equals -2 and 2 that has the same instantaneous slope. Well, if it has the same instantaneous slope, we've actually already looked at questions like this. If it has the same instantaneous slope, the tangent lines should be parallel, because parallel lines have the same slope. So something like that. So then find a point or points on the graph that has the same instantaneous slope. You know, we're estimating it's like 1.2 and -1.3. Now you could find those values exactly. You could find these points exactly by saying, all right, let's take the derivative function, which is 3x squared minus 2, and set it equal to 2. Because we want to see when my instantaneous rate of change is 2. So solving that, we get that x equals plus or minus the square root of 4/3, which is pretty close to what I was approximating. So what we showed is that there exist at least one, and in this case 2, points in between -2 and 2 that had the same instantaneous rate of change as the average rate of change on that interval. So there existed in between -2 and 2 at least one x value that had the same instantaneous rate of change as the average rate of change on that interval. Okay, let's look at one more example of this. So slightly harder graph, root x plus e to the x. So I've already graphed this, and my y values, or my x values, are going from 0 to 5, and my y values are going from 0 to 60. So again, if you'd like to, try to do this on your own. Otherwise, follow along with me. It says, so we've sketched the function. Find the slope of the secant line connecting 0, f of 0, which is the point 0, 1, and 4, f of 4, which is the point 4, 56.5. So the slope for the secant line connecting those is going to be the change in y over the change in x. Here's the slope, which is, let's see, 1. I think something like that. Yeah, 14.125. So that's my slope. And then it says find a point or points on the graph that has the same instantaneous slope. So again, if it has the same instantaneous slope, we're talking about a point whose tangent line is going to be parallel to the secant line. So where is that happening? That's happening roughly at x equals 3. So I drew the tangent line. Now, how would I find exactly where that exists? Well, I could find the derivative again, which is 1/2 x to the negative 1/2 plus e to the x. And I could set it equal to the slope of the secant line, but we're not going to do that here. But again, what happened? So on the interval from 0 to 4, there existed a point in between 0 to 4 that had the same instantaneous slope where the derivative equaled the slope. This is the idea, or this is moving towards the idea of the mean value theorem. The mean value theorem says that if a function is continuous on the closed interval a to b and differentiable, so you need to be able to take its derivative on the open interval a to b, then there exists at least one number c in between a and b, such that the derivative at c equals the average rate of change. And that's exactly what we've just been looking at. So let's use that mean value theorem. It says if a function is defined on the function or on the interval 1 to 3 by this function, show that the mean value theorem can be applied to f and find a number c which satisfies the conclusion. Well, here's a graph of what's going on. The red line is 4 minus 3 over x. And we know that at 1, my function equals 1. And at 3, my function equals 3. So the slope of this secant line is going to be the change in y over the change in x, which is 1. So therefore, I want to find a derivative. I want to find where my derivative of this function equals 1. So let's find the derivative function. F prime of x equals, well, just let's rewrite this as it's going to equal 3 times x to the negative 2. Now we need to be careful that that we can use the mean value theorem. So one of the key things is that it needs to be differentiable on the open interval. So this function, our derivative, 3 over x squared, the domain of my derivative is simply that x cannot be 0. Because if it were 0, it would make the denominator 0. So therefore, since I'm only looking between 1 and 3, f prime of x is differentiable on that interval between 1 and 3. So then we want to say, well, when does my derivative, 3x squared, when does my derivative equal 1? And solving that, we get 3 equals x squared, or x equals plus or minus root 3. Well, since we're looking between 1 and 3, it's just at square root of 3. And so the mean value theorem is satisfied here. In other words, in between 1 and 3, where the average rate of change was 1, there existed at least one place where the instantaneous rate of change was also equal to 1. All right, so use the graph of g to estimate the numbers on the interval from 0 to 8 that satisfy the conclusion of the mean value theorem. Well, from 0 to 8, we've got, if we draw the secant line, the mean value theorem says that between 0 and 8, there must exist a place where my derivative equals the slope of this, which is, well, um, negative 1/8. And we know that f prime of x is differentiable on this region. How do we know that? Well, we know that because the curve, this is it's a completely smooth curve, so there's no cusps, there's no points of discontinuity, so there's no reason for my derivative not to exist. So to find out where the values of x that satisfy the mean value theorem, we just need to find out, estimate places where the derivative has roughly the same slope. So down there, so roughly when x equals maybe 2.9, 1.1, and 6.8. And those are just rough approximations. But the idea being, on that interval in between 0 and 8, there was at least one, and in this case, let's get a different color. There needs to be at least one, but in this case, there were three. 1, 2, 3 places where the instantaneous rate of change is equals the average rate of change on that interval. Okay, so in exercise 3 to 10, determine whether f satisfies the hypotheses of the mean value theorem, and if it does, find all the numbers c in that interval from a to b that makes this true. Okay, well, let's do these one at a time. If we look at the first one, does it satisfy the hypotheses of the mean value theorem? Well, the derivative equals 2/3 x to the negative 1/3, which is the same thing as 2 over 3 cubed root of x. And this is undefined at 0, which means that it is undifferentiable on the interval from -1 to 2, since 0 is in that interval. So because my derivative is undefined at a point inside this interval, we say that it's not differentiable. So this doesn't satisfy the conditions necessary for the mean value theorem. What about 6? Well, in 6, just as a reminder of what that looks like, we've got an absolute value, and we know that at x equals 0, there's a cusp. Therefore, it's not differentiable at x equals 0. So it's not differentiable between -1 and 2. So this doesn't meet the qualifications necessary for the mean value theorem. Similarly, so the point of all these questions is just to make sure that the function is in fact differentiable. So in this case, f prime of x equals 1/3 x to the negative 2/3, which can be written as 1 over 3 cubed root of x squared. So again, this is not differentiable at x equals 0. However, because we're looking at the interval from 0 to 6, it only needs to be differentiable in between 0 to 6. So it's not differentiable at x equals 0, but it's differentiable for x values getting close to 0 up to 6. So here the mean value theorem is satisfied. So we need to find, let's show what this, um, let's find the value of c. Let's find out where do we have that exact instantaneous velocity that equals the average velocity or average rate of change. So in other words, we know that we have the point 0, comma 0 to the 1/3 and 6, comma 6 to the 1/3. So my average rate of change is 6 to the 1/3 over 6, which is the change in y over the change in x. And I want to know, when does my instantaneous rate of change equal that? So let's start a fresh page so that it's more clear. Remember, my derivative was, what was it? 1/3 x to the negative 2/3. And I want to know, when does this equal the average rate of change on that interval from 0 to 6. So we can solve for this. We get 6 to the 1/3 equals 1/3 x to the negative 2/3. Let's multiply by 3. We get 3 times 6 to the 1/3 equals x to the negative 2/3. To get rid of that negative 2/3, let's just raise both sides to the negative 3/2. So we get that x equals 3 to the negative 3/2 times 6 to the negative 1/2. Multiplying these, the 3's would cancel off. And just to see what that number actually is, we have 3 raised to the negative 1.5 times 6 raised to the negative 0.5. So it occurs at when x equals roughly 0.079. So what was that value again? 0.079. And just to be kind of careful with what we do, this value needed to be between 0 and 6, and it in fact is. Great. And now for the last problem. Looking at number 10, f of x equals 2 sine x plus 2 plus sine 2x. The derivative of that is 2 cos x plus cos 2x times 2. Now this is going to be differentiable everywhere because cosine of x, cosine 2x is differentiable everywhere. So it's differentiable on the closed interval from 0 to pi, so we meet that. So we need to find the, let's find the average rate of change, or the mean value. So the average rate of change. Well, we know that at 0, my y value is going to be 2 sine of 0 plus sine of 0. And sine of 0 we know is 0, so it's just the point 0, 0. And my other point at pi is going to be 2 sine pi plus sine of 2 pi. Well, 0, 0, so we get the point pi comma 0. So the average rate of change is going to be the change in y over change in x, which is just 0. So therefore, there must be some place on this interval, there needs to be some place on the interval from 0 to pi such that my derivative, my instantaneous rate of change equals 0. So let's find out where that is. So my derivative, 2 cosine x plus 2 cosine 2x must equal 0 at some place. Now, unfortunately, to solve this algebraically, we need to get into some double angle work. All right, so here we are trying to solve this, and as I said just a second ago, we're going to need to use some double angle identities. If you want, you could just graph this on your graphing calculator and see when it equals 0. But I think it's worth our time and worth the fun just to solve this by hand. So again, what we did, we took this function 2 sine x plus 2 plus sine 2x. The average rate of change on that interval was 0. We want to see when does the instantaneous rate of change equal 0. So we took the derivative. Here's the derivative. We're setting it equal to 0. And what we need to remember is that cos of 2x equals cos squared of x minus 1. Sorry, 2 cos squared of x minus 1. So from that, we get 2 cos x plus 4 cos squared x minus 2 equals 0. And this looks kind of ugly, but if we divide everything by 2 and rearrange it, so dividing by 2 and writing in descending order, we get 2 cos squared x plus cos x minus 1 equals 0. What do we do here? Well, let's factor it. So we get we're factoring it because it's a quadratic. We have cos squared. So think of cosine x as just your variable. So we get 2 cosine x minus 1 times cosine x plus 1 equals 0. And if you need to convince yourself, just FOIL. You can unwrap this, and you'll very quickly see that this factored is exactly this top expanded. But what that allows us to do is it allows us to set up the following. We get 2 cosine x minus 1 must be 0, and cosine x plus 1 must be 0. Okay, so cosine x must equal negative 1. Where does that happen? That happens when x equals pi, or when it equals 3 pi, 5 pi, but let's just leave it there, when x equals pi. And we get 2 cosine x equals 1. Cosine x must equal 1/2, and we know trig really well. This happens when x equals pi over 3. So these two values are when my derivative equals 0. Now, going back, we need to remember that we're only looking on the interval between 0 to pi. So therefore, we're going to have to get rid of that value because it's not between 0 to pi. Because we're looking for x between 0 to pi. Pi is not in between that. So where does this happen? At x equals pi over 3. And let's just look at a quick picture of this graph so that we have an idea, a true idea of what's going on. If we graph, making sure we're in radian. So we graph sine x, or 2 sine x, plus sine of 2x and we're going to look between 0 and pi. We see we start at 0, which we expected, and we finish at 0, which we would expect. So if I want to find the maximum, because the maximum is where my derivative is going to be 0. And this should be at pi over 3. Pi over 3 is just a little bit over 1. And we get 1 point. This is pi over 3. So that is right. And so that's where my slope is 0. My instantaneous slope is 0 because my average rate of change between 0 and pi is 0. In other words, I found a point where the instantaneous rate of change equals the average rate of change. Okay, so that's it for now.